Although the wave model of light explains many aspects of the behavior of light, several observations cannot be resolved by this model. Three of these are particularly pertinent to our understanding of how electromagnetic radiation and atoms interact. Number one, the emission of light from hot objects, referred to as black body radiation, because the objects studied appear black before heating. Number two, the emission of electrons from metal surfaces on which light shines, also known as the photoelectric effect. And number three, the emission of light from electronically excited gas atoms, known as emission spectra. We'll examine the first two during this video cast. So when solids are heated, they emit radiation, as seen in the red glow of an electric stove burner or the bright white light of a tungsten light bulb. The wavelength distribution of the radiation depends on its temperature. Red-hot objects, for instance, is cooler than a yellowish or a white-hot one. During the late 1800s, a number of physicists studied this phenomenon and tried to understand the relationship between temperature and the intensity of the wavelength. In the 1900s, a German physicist named Max Planck, P-L-A-N-C-K, solved the problem by making a daring assumption. He proposed that energy can be either released or absorbed by atoms in discrete chunks of some minimum size. This fixed amount of energy, or the smallest amount of energy that can be emitted or absorbed by an atom, was given a fancy name. They called this a quantum of energy. Max Planck, P-L-A-N-C-K, was the first guy to come up with this idea, and therefore an equation that related this amount of energy to the frequency of the energy has a constant in the equation, and that constant is called Planck's constant. Planck's constant is a very small number, and it is symbolized by the letter H, and it is 6.626 times 10 to the negative 34th joules times seconds. According to Planck's theory, matter can emit or absorb energy only in whole number multiples of h times frequency, such as HV, 2HV, 3HV, and so forth. If the quantity emitted by an atom is 3HV, for example, we see that 3 quanta of energy have been emitted. A few years after Planck presented his quantum theory, scientists began to see its applicability to many experimental observations. Along came Albert Einstein, and he used Planck's theory to explain what's called the photoelectric effect. The energy, measured in joules or kilojoules right here, is related to Planck's constant times the frequency of that electromagnetic radiation. Einstein used this to explain what's called the photoelectric effect. Light shining on a clean metal surface causes electrons to be emitted from the surface. A minimum frequency of light, different for different metals, is required for the emission of the electrons. The reason that Einstein was interested in this is because it wasn't the same for every single metal. He explained this by saying that there was a stream of tiny energy packets that struck this metal. He called these photons and said that an energy of a photon is equal to Planck's constant times the frequency of this photon, or of this radiant energy. We can use this equation E equals h nu, or Planck's constant times nu, to solve various energy of electromagnetic radiation questions. Let's look at sample exercise 6.3, which, if you're in Brown LeMay, it's on page 218. If not, you can follow along with the question. It says, calculate the energy of one photon of yellow light that has a wavelength of 589 nanometers. So write down our given, 589 nanometers, and use it to find E, or find energy. First of all, the equation we need to know is that E is equal to H times nu. You can take this and put it into a triangle, just like we did with C equals lambda nu. E equals H nu. We want to find this to help us solve for E by multiplying it by H. Notice we know the wavelength, but we don't know the frequency. In the previous video cast, we learned that wavelength and frequency multiplied together equaled the speed of light. And so we could solve this by saying, what's new? What's new is equal to C over lambda. C, of course, is the speed of light, 3 times 10 to the 8th meters per second. And the wavelength is 589 nanometers. We need to convert the nanometers to meters. The nanometers will cancel with one another, meters will cancel with one another, and we're left with 1 over second, or per seconds, or hertz for our frequency. Take the frequency and now multiply it by Planck's constant. Frequency times Planck's constant. Notice the seconds cancel, and you're left with the energy in a photon. Now, you might encounter a type of problem that asks you, how much energy would there be in a mole of these photons? Well, of course, photons are just a particle, and in a mole of anything, whether it be photons or atoms or molecules or ions, there are 6.02 times 10 to the 23. And since this is the amount of energy in one photon, we could multiply this number times 6.02 times 10 to the 23rd. The photons would cancel, and we'd end up with how many joules there are in a mole of photons, which would be 2.03 times 10 to the 5th joules in a mole of photons. Good luck with your E equals H nu and C equals lambda nu equations.